Hello and welcome. In this worked example, we'll be looking at question number 2 from the February-March paper 22 from 2018. So the question starts with explain what is meant by work done and kinetic energy. So this is kind of like knowing our definitions. The work done is equal to the force times the displacement. So we might sort of think in terms of equations, work is force times displacement. But remember, the full form of this equation is times the cosine of the angle theta, where theta is the smallest angle between these two vectors. So it's a dot product. Work is a scalar product. You multiply two vectors and get a scalar because you're only taking the horizontal component of force, or only the component of force that acts in the direction of displacement contributes to work. So you could kind of explain what is meant by work done as force times displacement, but only the component of force acting in the direction of displacement. Or you could say force times displacement times the cosine of the angle between them. That's how we sort of calculate work done. The product of force and displacement and the cosine of the angle between those vectors. It's really the smallest angle. So you remember if there's like a force this way and we're displacing the thing this way, so it's only like this component, the F cosine theta, that's the only one that contributes to work because it's in the direction of displacement. The angle between them would be this angle here, the smallest angle, right? There is an angle like this, the other way sort of around the circle, but that's not the angle we plug in. So it's the smallest angle between those two vectors. What is meant by kinetic energy? So this is energy of motion. And we could say that kinetic energy equals 1/2 mv squared. So you want to kind of explain what is meant by it. So it's the energy that an object has due to the fact that it's moving with sort of non-zero velocity. And we can calculate what the kinetic energy is, just to sort of remind ourselves what's important, 1/2 mv squared. 2 marks for your definition. So hopefully everybody out there studying is being mindful of going through all of the vocabulary, know your definitions, know all the laws, be able to state them to earn this low-hanging fruit. The definition should really be sort of marks that are well within reach as long as you're taking some time to study it well. Question goes on. A leisure park ride consists of a carriage that moves along a railed track. Part of the track lies in a vertical plane and follows an arc x, y of a circle of radius 13 meters, as shown. The mass of the carriage is 580 kilograms. At point x, the carriage has velocity 22 meters per second in a horizontal direction. The velocity of the carriage then decreases to 12 meters per second in a vertical direction at point y. For the carriage moving from x to y, show that the decrease in kinetic energy is 9.9 times 10 to the 4 joules. So when we're trying to calculate a decrease in kinetic energy, sort of the most straightforward way is say, well, this is a change in kinetic energy. And we may recall that, the work done equals the change in kinetic energy. It's not a coincidence that we just defined work done and kinetic energy. And there's a theorem in physics known as the work kinetic energy theorem. In my opinion, the most efficient path to the solution here is to really just focus on the right side of this and think about what is a delta, a change in kinetic energy is going to be the final kinetic energy minus the initial kinetic energy. So the final kinetic energy is just going to be 1/2 mv squared, and the initial kinetic energy is going to be 1/2 mu squared, where we like to use u for initial velocity and v for final velocity in this course. I'll make some subs. Now you could factor out the 1/2 m, if you prefer. You can just, plug in everything. I kind of like to keep the mass in each term to calculate what is the kinetic energy, get a number in joules for this, get a number in joules for that, rather than like factoring out the common 1/2 m and then just get sort of the final answer. So in other words, I want to know sort of the values along the way. So what is 1/2 mv squared? Let's make some substitutions down here. The mass was 580 kilograms. We need to have kilograms of mass to get joules of energy, so there's no conversion needed there. The velocity is also in nice friendly units. Its final velocity, remember, was 12. It decreased down to 12, so it's 12 meters per second squared. Minus the 1/2 580, the initial velocity was 22 meters per second. Don't forget to square that. So it's going to be a negative change. In other words, there's a negative change in kinetic energy. It's okay to have a negative energy. That just means that the work was sort of being done against it, right? So like gravity was doing work to slow this thing down because it's sort of fighting gravity. So we'd expect it to sort of slow down because gravity was doing work against it. I'm going to calculate each one separately. So 580 divided by 2 is 290 times 144, which is 12 squared. So the final kinetic energy is just 41,760 you should calculate. The initial kinetic energy with a velocity of 22, square that, times 580, and divide that by 2. So it started out with 140,360 joules of kinetic energy, but it decreased to this. And so again, we would expect sort of a negative answer because our final is less than our initial because of the velocity. And so we'd have 41,760 minus 140,360. And that gives us a change of negative 98,600. And I don't think it's necessary to sort of hold on to the negative sign. You know, like it is a scalar, so what we really care about is, you know, sort of the magnitude here. There was a decrease of 98,600. And again, the way to sort of interpret this is just to say, well, you know, work was being done against this thing. Gravity was doing work in the opposite direction. So it goes right back to that idea of the cosine theta. If we think about, you know, gravity can only do work in this direction, right? It only exerts a force down. So only the component of force that acts in the direction of displacement contributes to work. So the force of gravity is always acting down. You could kind of imagine at each sort of moment along the path until it really gets to this sort of vertical. Now all the work is being done against it, right? But gravity sort of always goes straight down. So gravity is sort of always doing work sort of along this way. So 98,600 or negative 98,600. When we check the mark scheme, we might find that they've rounded that up to 99,000, and they probably don't have the negative sign, but we'll look at that before the end of this. All right, so that's the change in kinetic energy. Now we want to calculate the gain in gravitational potential energy. All right, so if we look at the figure carefully and we're trying to just calculate the gain in gravitational potential energy, there's, I suppose, a couple of ways to sort of think about this. And one of the clues that we want to look for in the question is, do they tell us anything about like friction is negligible, or, you know, we can assume that there's no friction? As we scour the wording of the question for that kind of language, we don't find that it's there. Okay, so in other words, we can't just say, hey, all of the kinetic energy it had got converted into potential. We might have lost some energy along the way, right? Because this is a track, right? A railed track. And so there's probably friction between the wheels of the carriage and the track itself. There's heat losses. And so we can't just assume that the difference in kinetic energy is all showing up as potential energy. The simplest way to calculate that would be to say, what we just calculated here is this, right? Like because energy is neither created nor destroyed, we started out with a certain amount of kinetic energy. We have less than when we're done, right? There was a difference of 98,000 or whatever. That's all the potential energy, but that's too simple for this, okay? That's just saying that would only be true if they said friction is negligible, there's no energy losses, or you can assume that all of the kinetic energy is converted into potential. And if that were the case, it probably wouldn't be a 2-mark question. it would just be kind of like they're expecting you to recognize that, oh, energy is conserved and the loss of the kinetic is the gain in the potential. Rather, we need to rely on sort of a different way to solve this. I think, again, we'll look at a Mark scheme and say, oh, it's just the same number, just write it down again. I don't think so. I think they would really have to tell us that friction is negligible or zero, or we can assume that, you know, all the energy losses here show up here. Rather, I think we're given enough information to just calculate it directly. You know, if we look at what is the increase in Earth's gravity field, it's 13 meters, right? So in other words, if this thing starts at point X, 13 meters lower, its distance traveled along the way, it's losing friction all the way there. But all that gravity cares about is the direction that this thing is going sort of against the displacement. And so when we think about where that equation comes from, the potential energy due to gravity equation, we know it's mgh, but it's really just the general force times displacement. Again, in the direction of the force acting in the direction of displacement. And so as the inertia of this thing sort of, you know, pushes it up the ramp here, right? Gravity is fighting it straight down. So we're only doing work against gravity in the vertical direction, or gravity only does work on this thing, again, in the vertical direction. And so the force is the weight mg, and the displacement, you know, sort of in that direction again is the height. And so all we care about is this vector, the vertical sort of vector. And so with that thinking in mind, that's enough to really calculate the gain in the gravitational potential energy to say, well, we started out at a height of 0 down here at X, and then we increased a 580 kilogram mass in Earth's gravity field, 9.81 newtons per kilogram. That gives the weight of the carriage. And we know that we displaced it 13 meters in Earth's gravity field. And again, we don't really care about the whole path, right? Like that arc of the circle. All we care about is the component, you know, of displacement, like in the direction of force. You could word that either way. You say the component of force acting in the direction of displacement. Here, it makes more sense to kind of say the component of the displacement that's, you know, sort of in the direction of the force, right? Because we're only caring about sort of the component that's vertical. So 580 times 9.81 times 13 gives us 73,000. Let's write this up here. 73,967.4. And I look at that and go, either 74,000 or 7.4 by 10 to the 4, right? So we kind of round this to 74,000 joules or 7.4 by 10 to the 4, put in scientific notation. Note that the gain or the decrease in kinetic energy was more than this, right? So they weren't just equal. We actually don't gain as much as we've lost here. But energy we know is neither created nor destroyed. We can kind of anticipate perhaps what the next calculation, like I might ask us about, try to explain the energy losses or something like, or use your answers in these two to explain, you know, how much is lost due to friction, something like that. Let's see if they go that route. It says, show that the length of the track from X to Y is 20 meters. Okay. So I guess the way that I would do this would be to kind of complete this circle and say that we'd have the total circumference would be 2 pi r, and we know what r is, and it looks like we've just got a fourth of it. So if we take the total circumference and we just divide it by 4, I think that's how we'll solve it. So we should just be able to take 2 divided by 4 is a half. So if we just do pi over 2 times r, and so hopefully that's 20. So r is 13 times pi equals divided by 2, and sure enough, that's 20.42. Because this is exactly 13 meters to get to here, and this is exactly 13 meters to get to here, 13 meters to go up, 13 meters to get over, right? So what is a radius? They tell us it has a circle of radius 13. It's the distance from any edge to the center of the circle, right? So we can kind of say, okay, we've got a quarter of our circle here. Or do we? Oh yeah, this is 90 degrees. That's the big clue. There's a 90-degree angle right there. And so we could sort of say, okay, well, that's 1/4 of the circle, because the whole circle is 360 and that's 90 degrees right there. So well, they could put this a little bit lower there, but no, it's exactly 90 degrees. So it's indicated by that. So this working will get you there. Just take the total circumference and divide it by 4 or multiply it by 1/4. So computationally, it ends up being pi over 2 times r, where r is the radius 13 meters, and that works out to be 20.42 is indeed about 20 meters. Use your answers in B1 and B2. Okay, so this is B2. Okay, B1 was this gain in gravitational potential energy. So you may recall that that was our 580 times our 9.81 times our 13. This was our 73,967, or we rounded it to 74,000, right? 73,967 was the calculator value, and we recorded our answer sort of like this. So it says use your answers in B1, that's this one, and B2, that one, to calculate the average resistive force acting on the carriage as it moves from X to Y. So here's our friction, okay? And I said, remember, anytime there's sort of like an energy budget where it's like, hey, we just showed that we've decreased our kinetic by this much, but we've only increased our potential by less, we're missing some energy. And they're probably going to want you to account for it because it's such an important law, the law of conservation of mass energy. So if we recognize that the energy was lost as heat, as friction with the sort of wheels of the carriage running along the rail there, then we could say, okay, we know that there was some work done by friction. Work is force times displacement. And here we just sort of say at every sort of moment along the path, friction is a non-conservative force. And so it's like the path that it takes sort of matters there. That's why we have to actually know the displacement. In other words, this was the actual path along the track where every one of these, sort of 20 meters along the way, it was losing some energy. Okay, so some work was being done by friction. Okay, that's why there's less energy that's showing up. So the work done by friction against it should account for the difference there. So we could say, I really feel like we need more than just our answer in B1, because this is sort of the gain in potential energy, but that's not, equal to the work done. That's sort of what we did with gravity. I feel like we need to use both of the answers. Like we need the difference. In other words, the difference between the kinetic energy we got, and maybe both of those answers are part of one. That's, I guess, what I should be very clear about. So yeah, so see, both of these answers were one. Okay, so it's like this is the famous, multiple part question of ACE, physics here. This is all question 2, right? 2A, 2A1, 2A2, 2B, 2B1, 1, 2B1, 2. So 2B1, 1, and 2B1, 2, right? Both of those were sort of the answers we need to consider, which makes a lot more sense because we're sort of accounting for missing energy. So let's sort of remind ourselves what all that was. So we had the value that we first calculated for the kinetic energy copied down. So my working is fleeting here on the whiteboard. It's like 99 or 98,600. That was our decrease in kinetic energy. So you might say, well, all of it should be potential energy then, but it wasn't, right? There was only 73,967 joules of gain in potential energy, which means we're missing, we're missing 24,632 joules of work, of energy that friction must have that friction did, right? Friction did this work. So there's the work that friction did. We're solving for what was the average force of that. And again, it's an average because, all along the way, all along these 20 meters. And so that's the actual displacement from the path XY. So we'll take our 24,632 divided by 20. And some of these values I'm just keeping in my calculator, so it may be a little bit different, but we'll round it sort of all at the end here. So I get a calculator value of 1,231. Newtons, right? Because this is a joule, so a joule is a Newton meter. So a Newton meter divided by a meter is a Newton of force. And so you get 1,231, or we could round that really to two significant digits and say 1,200 newtons. So I'll clear that off. You get 1,200 newtons as the average resistive force acting on the carriage. It goes on to say, describe the change in the direction of the linear momentum of the carriage as it moves from X to Y, and then determine the change of the determine the magnitude of the change in linear momentum when the carriage moves from X to Y. So momentum is a vector, and we could say that there's a certain momentum in this direction. It has mass 580, it has velocity 22, but then as it sort of moves up, gravity is doing work against it, friction is doing work against it, right? Both of those things are sort of stealing away some of the kinetic energy and therefore decreasing the velocity. We know that the velocity decreases all the way to 12 meters per second by the time it gets here. The carriage is also pointing in a vertical direction. And so the momentum, the linear momentum that it possessed horizontally has been converted into sort of vertical momentum. And that's because the track is exerting a force on it sort of all the while. So we want to kind of think through this with sort of the physics concepts in mind. Force is the rate of change of momentum. We can clearly prove that this thing has changed its momentum because its velocity has changed. Its mass hasn't changed, but because its velocity did, there's some acceleration, right? Slowing down. The track is exerting a force sort of normal to this all the while, right? So it's sort of like, as this thing moves this way, the track is sort of pushing it up. Gravity keeps sort of pushing it down. So when we talk about describing, I'm interested to see sort of how the mark scheme sort of addresses this. Describe the change in the direction of the linear momentum. It's somewhat, the change in the direction of the linear momentum. So the linear momentum is still sort of moving, this, in other words, its linear momentum is what sort of carries it all the way through. Like we could just kind of imagine, even though this is the vertical direction, like this is just kind of like one path that it's following, this way. So like it has momentum in this direction, and then the track just sort of curves this way. So in order to change its momentum, a force has to be exerted. And so there's like a normal force between the track that's being exerted there. I'm not sure how exactly I would put that into my own words, but this would be a good one to sort of, take a look at the mark scheme. And once we kind of, think through the ideas and say, okay, we basically understand that it's the direction of its linear momentum has gone from horizontal to vertical. Describe the change, should we just kind of state it like that? Like, horizontal momentum or the velocity vector is pointing horizontally, it changes to vertical. And then when it says determine the magnitude of the change, is this where we should just kind of use this equation that I've got off to the right there? So let's take a look at that. If we do, we know that a force was exerted on it, okay, but they only ask us to calculate this numerator. They really don't tell us anything about the the time, although I suppose if we had the force from before, we could sort of figure that out, but we just can kind of treat this the same way that we did, I'm sorry, the kinetic energy, which is final minus initial. So the final momentum is going to be mv, and the initial momentum is going to be mu, but again, this direction. So is it okay that we just sort of say, okay, well, the line that we're considering is a curved line, right? And so, or do we have to account for the fact that, well, it went from a certain initial velocity to basically zero in the direction that it had its initial velocity in. In other words, if it had momentum here, because it has velocity this way and mass this way, but then we say, well, what's the final momentum in that direction? And it no longer possesses any velocity in that direction, right? Like the velocity in that direction went to zero, then the change in momentum would just be, well, however much momentum did it start with? So one possible answer to this would be if we say, yeah, how are we dealing with this direction? So here they're sort of asking you, really think about describing the change in the direction, because if you interpret it like, well, this is just a line that it's going on. In other words, I'm talking about the change in momentum along this axis here. But the fact that like, well, gravity is doing work this way, right? Makes it a little bit trickier to sort of reason through. So one approach is to just take all the momentum that it had, the 580 kilograms of mass times its 22, it was 22, right? Yeah, it went from 22 down to 12, I think. 12 to 22, right? Started out at 22. So if we just say it had this much momentum in the x direction initially, then its final momentum in the x direction is zero, right? Because all of its velocity is now vertical. In other words, the track had to exert a force on it to change its direction, right? So any change in velocity is an acceleration, both slowing down and the change in direction. So one way to solve this would just be to take 580 times 22, and that would give a change in momentum, again, because we're saying it goes to a final momentum in the x direction is zero. So we're saying like, if we just consider it like this is the x-axis, so its initial momentum was 12,760, and then all of that momentum is gone in the x direction. We've sort of transferred it into the y direction. The other way that students might approach this is to sort of be mindful of, well, its final momentum, it still had 12 meters per second of velocity. But remember, all of that velocity is going in the y direction, okay? So the scalar nature of energy meant that we didn't really care what direction the velocity was in, because the direction, like if we use a sign convention with kinetic energy, we square it, right? So the velocity gets squared anyway, kind of doesn't matter. So I'm leaning towards this as maybe the correct answer, but it's 3 marks and that was kind of straightforward. You know, do we have to sort of think about it like this again, just sort of like along this line, whether it's curved or not, it has a change in velocity. And so, you know, what is the change in momentum? If we don't say, well, it ends up with 0, it still has sort of velocity in this direction. If you define sort of the direction as a curved line, because sometimes like with an Atwood's machine, we got a pulley and we got like a mass suspended from another mass, and we sort of say, well, which direction is this Atwood's machine going to accelerate in? It's kind of like, well, this direction is down, this direction is up, but it's really the same direction, right? Like the Atwood's machine is moving this way. So it's kind of like, well, this whole thing is going in this direction, even though up and down, they look like opposites, the whole thing is moving along that direction. And that's kind of, I guess, I'm thinking of like an Atwood's machine, kind of like I like to draw, that's the positive sort of direction of the Atwood's machine, the direction it's going to accelerate in. It's like, well, there's my direction right there. And so the other way to sort of approach this would be to say the 580 kilograms times the final velocity of 12 minus the 580 times the initial of 22, and then it's sort of again, it could be a misinterpretation because that's no good. We need to sort of separate those, and this was the better interpretation. We'll give ourselves feedback in just a moment, but let's kind of put both answers up there. 580 times 12 is 6960. And 580 times 22 is the number we already got there. And so 12,760, that's negative. We add 6960 to it, and we get, you know, like negative 5,800. So it's like we end up having a force that's being exerted against the direction of its motion, right? It's like this negative sort of change in momentum. So that means that if we divide by time, we get a negative force. And so if the velocity is this way, then the force is going to be sort of opposing it, or it's like the component of this force that's acting against it all the while, right? Until eventually it's sort of moving just vertically. All right, let's take a moment now to give ourselves some feedback on this. So I can conveniently change this QP to our scheme MS. Click that, do that. And now we've got question number 2, I believe we were just looking at. So we've got force times the distance moved in the direction of the force. Note how they've sort of captured that cosine theta by saying only the component of force in the direction. The energy of a mass or a body due to motion or speed or velocity, right? So energy of motion, 1/2 mv squared. Oh yeah, it said to show this, right? And I was like, what do we got? Oh yeah, we got 99, you know, 9.9 by 10 to the 4. But the change in potential energy, you see the way they calculate it, they just use the 13, okay, 7.4 by 10 to the 4. So far, so good. The length, they just do it, you know, 2 pi r over 4, right? Dividing it by 4, there's your 20. The work done against the resistive force is the difference in the energies, and then divided by the 20 to give you 1,300. From horizontal right to vertical up, or 90 degrees. So they have the momentum is 580 times 22 or 580 times 12. The change in momentum so what have they done here? They've got the, again, they're just sort of, they're using both values. And so is this the, that doesn't agree with either answer that we got, right? That's the final. Of course, like, the reason why I intentionally made this mistake in this video was to really highlight for you all the important nature of vectors. And so let's take some care with this now. Because if you just look at the mark scheme, you like give myself feedback. You're like, I know where these numbers came from, but what have they done here? So we need to say the change in momentum is the final minus the initial. Okay. The final momentum, okay. The final momentum is going to be your mass times the velocity. So we have mass times velocity, okay, minus the initial. But the initial, okay, if we say that this velocity is up, then we have to sort of keep track of it. In other words, this plus sign sort of came from subtracting it, but actually none of this is the best way. Here's what we got to do. We got to say initial, right? This was the initial momentum vector. Final, okay? And again, we kind of got this from horizontal to vertical, right? Or up to 90 degrees. Remember that if we have vectors, how can we calculate them? Well, we could, if we were adding them, we put them head to tail, right? So I could say, there's my final here's my initial. And if I just were to sort of put this one like this, head to tail, and I connected the dots, then that would be the sum of, you know, the initial and the final. But if I want to subtract them, I could put them tail to tail and connect the dots, or I could just say, well, if PI plus PF is like this, but I want, I'm sorry, PF minus PI, so I'm going to take my final momentum vector here, and instead of adding my initial velocity vector to it like this, I'm going to subtract it, which means it's going to point the opposite way. And so that is the change, right? So there's my final. That's my negative initial right here. And so what they've done is they've calculated just the momentum going vertically. And they've said the momentum vertically is 580 times 12. The momentum initial was 580 times 22. Okay, but we have to solve for this hypotenuse right here, right? Because the difference between them is when we connect the tail of the first one to the head of the last one. Remember, subtracting is just like, that's why I've taken this initial velocity, which was definitely pointed that way, but I'm subtracting it, right? So the negative of it, it flips over this way. And so that's why you can kind of see Pythagoras' theorem in this working here, right? So it's the square root of this squared plus this squared, right? So they've taken this quantity squared plus this quantity squared, and then take the square root of it because they're solving for the hypotenuse here. So this is the only way to sort of deal with it, right? When you've got vectors like this, right, we have to use Pythagoras' theorem to take the difference. It's not as simple as like, oh, we've started in this direction and then we ended in the opposite direction. It's, as the mark scheme suggests, is this 90-degree change. So I'm sure if we were to sort of, you know, like it suggests here, you just kind of work through that, and then you're solving for the hypotenuse of this right triangle using Pythagoras' theorem. So the final and initial end up being at right angles to each other, and we know how to sort of solve. We've got that. We use Pythagoras' theorem, and so that's the sort of final solution. I think I missed the mark on these. Really these three here, and I'd probably take away. So I'd give myself 9 out of 13 on this one. Giving myself feedback. That's a, you know, 70% C. That's pretty good. All right. And we'll see you next time.